Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering.
In VLSI design, a library serves as the foundational database that holds pre-characterized information of standard CMOS logic gates. Library contains characterized models, using which a design can be simulated, even before its fabrication. Logic gate model design involves various steps like Boolean form functional expression, CMOS level circuit, stick diagram, and the physical layout creation, etc. In this video, we will have an overview of Boolean expression to stick diagram processing steps involved in a logical library model creation. So let's get started. Various steps involved in creating a logic library are discussed below. Identify appropriate MOSFET SPICE models, that includes relevant, material, processing, parasitic and second-order effects. Using SPICE syntax, create desired CMOS transistor level, functional schematic. Using SPICE models, simulate the CMOS schematic for functional verification. Using relevant test setup, evaluate CMOS gate circuit for static, dynamic and power characteristics. Create linear gate models for fast and approximate simulation, and also create nonlinear delay models for accurate simulation. Create gate identification name, symbol and include the extracted characteristics parameters. Repeat the above process for different functional gates and build a library. In digital VLSI design, the physical library forms the backbone of the place and route flow. As shown in the figure, the library design consists of various stages that start from Boolean function and ends up creating a physical library. In this video we will restrict our discussion to the Boolean expression to stick diagram flow. The Boolean function is made up of logical variables, functions and specifies a logical functionality. The Boolean expression is converted into a CMOS level schematic diagram. Using the SPICE level models and simulated to evaluate the functionality. The processing fabrication layers are color-coded, and using them, the schematic is converted into the stick diagram. Boolean expression describes a logic function using logical variables and logical operators. Boolean expression derived from sum of products and product of sums for high and low outputs. Use canonical form or simplified expressions. Minimize the expression using K-map or other algorithms. Optimize for transistor count, delay and power parameters. Implement expression into a CMOS diagram using the pull-up and pull-down network. A transistor SPICE model is a virtual device presented in mathematical form. It exhibits the device electrical characteristics, taking into account the device parameters like material characteristics, process parameters, geometry and the device parasitic. A FET model is a mathematical representation of the device electrical behavior under various operating conditions and is used in circuit functional simulation. Model enables designer to simulate the circuit performance even before prototype fabrication. A typical MOSFET SPICE model is shown in the figure. A typical PMOSFET SPICE model is shown in the figure. For a MOSFET, the SPICE model defines its electrical behavior using physical and empirical parameters, allowing accurate simulation of its performance in a circuit. Models are classified based on several factors like by technology node, validity of in-out parameters, the parameter complexity being considered, etc. The level of a MOSFET model in SPICE indicates the complexity and type of the mathematical model used to describe the behavior, taking into consideration the phenomenon like short channel, velocity saturation, leakage currents, etc. The level indicates the model accuracy, simulation speed, and relevance to actual silicon behavior. Lower levels like 1 to 3 simple models are meant for education or older technologies. Applicable technology node like micron or nano level that indicates the technology or feature size. Device's physical structure, geometry, electrical properties, parasitic elements etc. influence the device parameters and are included in the device modeling. Some of the parameters' impact is explained below. Physical dimensions like W and L of the device will impact the device current capability. The gate oxide thickness influences the gate capacitance and thereby the device current capability and threshold voltage. Substrate doping influences the body effect. Other parameters like threshold voltage, transconductance gain, mobility, length modulation, parasitic capacitances etc. are influenced by various factors shown in the table. Voltage-operated MOS FETs are used as logic switches and realize logical functionality. N and P MOSFETs connected in different configurations implement different logical functions. N or P MOSFET operating in common source configuration acts as a simple order. Series MOS switches implement logical and operation. Similarly, parallel MOSFET switches implement a logical or operation. The figure shows the CMOS logic switch operating in different configurations and their logical functionality is presented through the truth tables. CMOS logic gate circuits are built using combination of P and NMOS transistors that operate in complementary configuration. CMOS transistors operate in common source mode and provide phase inversion, which is an integral part of a CMOS structure. Desired logic function is implemented using pull-down NMOS switches. Its complementary function is created with pull-up PMOS switches and the CMOS logic gate produces inverted desired logic function. PMOS pulls the load towards supply VDD and NMOS pulls down the load towards the ground VSS. CMOS loads being capacitive in nature, PMOS provides charging and NMOS provides discharging currents and create dynamic characteristics. PMOS acts as an complementary, active load to the NMOS switch, hence at any given point of time, only one transistor conducts and minimizes standing or quiescent current and reduces static power dissipation. Stick diagram of a CMOS logic gate is a design rule-friendly, dimensionless layout structure. Stick diagram is an intermediate form between schematic and the layout. It simplifies the circuit to physical layout design transition. It ensures design routability, optimizes area, and early detects errors, if any. It is created by using color-coded lines of fabrication layer and symbols. The line diagram identifies components' orientation and interconnects routability. The design flow starts from Boolean expression and is converted into CMOS level schematic diagram. Using FET models, the circuit is characterized and converted into physical layout structure. In physical design, layout design refers to the geometrical representation of different layers of the chip. Each layer corresponds to a specific material used in chip fabrication. The layout layers are sorted out, masks are created and are used in layers processing. A typical processing layer's color convention adopted in drawing the stick diagram are, as mentioned below. NMOS diffusion layer by green. PMOS diffusion layer by yellow. Gate polysilicon by red. Metal normally drawn by blue. Contact identified by X, that is cross. Via with two enclosed different colored squares. N-well or P-well implant by dotted outline usually shown for PMOS. Following are some of the conventions adopted in drawing the stick diagram and are as mentioned below. Same layers crossover represents electrical contact or connectivity. Dissimilar layers crossover does not create any electrical contact. Dissimilar crossover layers electric contact is created by dot or X. Polycrossing diffusion creates a MOS transistor. Poly-crossing AN diffusion creates a NMOS transistor. Poly-crossing AP diffusion creates a PMOS transistors. Stick diagram of a CMOS inverter is a dimensionless layout. It uses colored lines and symbols to represent the structured layers of CMOS gate. Following are the steps involved in creating CMOS inverter stick diagram. Draw two horizontal widely separated horizontal lines for VDD and VSS power supply and also an imaginary line in the middle that separates into two top and bottom equal regions. Place PMOS in the top region and NMOS in the bottom region. Create widely spread out input, output and polymetal contact pins on the imaginary line. Connect the source pins of PMOS to VDD and NMOS source pins to VSS power lines. Connect both MOSFET gates with poly interconnect that also passing through polymetal contact. Using metal, connect polymetal contact to the input pin A. Using metal, connect both the drains pins and extend it to the output pin Y. Create text for VDD, VSS, input pin A and output pin Y. Generate cell boundary that encloses all the stick diagram elements. The physical dimensions of cell boundary represents length and width of the cell. Compare and confirm faithful transfer of components and connectivity between schematic and the stick diagram. This process helps to visualize the physical structure of the inverter before actual layout design, ensuring logical and electrical correctness. A NOR gate produces a high-state logical output only when both the inputs A and B are at low logic level state. Pull-down network consists of two parallel NMOS transistors. When either of the inputs are high, NMOS conducts and pull output to low-level logic state. The pull-up network consists of two series PMOS transistors that are controlled by inputs A and B. Both the inputs must be low to create high-level output. Adopting similar sequential steps adopted for CMOS inverter stick diagram drawing, the CMOS NOR gate stick diagram is realized. Pull-down network consists of two NMOS series transistors. When both A or B at high level causes, NMOS transistors conduct and pull output to low logic state. The pull-up network consists of two parallel PMOS transistors that are controlled by inputs A and B. Both must be low to create a high-level output level signal. Adopting similar sequential steps adopted for CMOS inverter stick diagram drawing, the CMOS NAND gate stick diagram is realized. Following are the steps involved in creating a stick diagram of a complex Boolean function. Minimize and optimize the Boolean expression. Identify the logical inputs, A, B, a bar and B bar. Identify logical operators, NOT, and AND/OR. Create sub-blocks like inverters, series chain sub-blocks, parallel chain sub-blocks. Create pull-down network blocks. Depending on the functionality, implement NMOS logic pull-down network. Create pull-up network blocks. Depending on the functionality, implement PMOS logic pull-up network. Join pull-down network to VSS and P pull-up network to VDD. Join other end of pull-up and pull-down network and create output Y. Identify and mark input pins. Create text for pins and create cell boundary. Create the stick diagram as explained earlier. The standard in a standard cell refers to the fixed and consistent attributes across all cells in the library. That includes the following. All cells should have uniform vertical height, so the common VDD to VSS rail can be routed. The cell width is variable and is defined by design complexity. It also has to adhere to the routing grid pitch design rule. Both N and PMOS transistors are to be aligned vertically. Both the transistors are distributed evenly and placed in horizontal orientation. Power rails are to be so designed such that they can be shared with neighboring standard cells placed. Input and output pins are to be evenly placed so that they are easily accessible for routing tool and minimize routing congestion. Layers of pre-defined colors are to be used in implementing their corresponding schematic elements. Routing within the cell is to be implemented by metal 1 and poly only. Poly, being a high resistive material, restrict its usage in the sticks diagram drawing. While creating CMOS gate stick diagram, special attention is needed due to the circuit complexity and in transistor placement. Below are some of the precautions that ensure layout compliant stick diagram design. To visualize the transistor level schematic, break the complex logic expression into subblocks using basic gates like AND or NOT gates. Create the desired logical functionality by employing pull-up and pull-down network. Join the pull-up and pull-down networks to create the stick diagram of the design. The stick diagram shown in the figure is for conceptual purpose only. However, in practice, stacking of transistors are to be avoided. For complementary inputs, provide inverters or check if they are available externally. Use consistent color layers in drawing stick diagram. Avoid poly-crossing metal, which would complicate the fabrication process. Indirect adherence to design rules in drawing stick diagram, symmetry and correct mapping of sticks to the schematic will ensure functional and performance of the fabricated layout that is called a standard cell. Thanks for your time. Hope this video has been helpful in appreciating the importance and methodology of creating a CMOS gate stick diagram. In the upcoming video, we will continue and create the physical layout using the stick diagram. Thanking you once again and hope to meet you in the upcoming video. Bye for now.